Okay, today's lesson is on elastic and inelastic collisions, and really all it is an add-on to what we've already done before with momentum. So what we're dealing with is collisions, and we're wondering if energy ends up being conserved or not as well. So the first thing that we've got to understand is if we're dealing with subatomic particles like atoms and electrons and things like that, is probably the only case that comes close to where kinetic energy is conserved. So by that I mean the total kinetic energy of all the particles before the collision has to equal the total kinetic energy of all the particles after. So much like we did with momentum, but now what we do is we check with kinetic energy. So remember, with kinetic energy we use so our formula for kinetic energy is 1/2 mv squared. So what we're talking about is that the 1/2 mv squared for each particle or object before the collision adds up to the same total after the collision. And Einstein said that all energy is conserved. It gets transformed from form to form. So what we have to be clear on here is in a collision, energy is conserved. The total energy still stays the same. But when we're talking about elastic and inelastic collisions, we're only worried about the kinetic energy. So most collisions will always be inelastic. We're not going to get total kinetic energy being the same before and after. So what we call these collisions are inelastic, and usually it means we have some sort of amount of kinetic energy being lost. So it could be heat due to friction, car brakes, that kind of thing produces heat. It could be sound. If you hear a car crash, some of that energy gets changed to sound. Could be light in terms of things sparking or whatever, or it could be just bending the shapes, like in a car accident the tin gets bent and twisted and all that, so that requires energy to do that. So because we're using up the energy, it ends up being inelastic. And there's a range. If you have objects that collide like pool balls or curling rocks, something like that, very little energy is lost, so it's still inelastic but quite efficient. If it's a rock being split up or a car accident or something like that, most of the energy ends up being lost, so there's not too much left over at all. Make sure you're clear that in every situation momentum is still conserved. So no matter what, we always still have conservation of momentum, so we can use all of our old formulas. The only thing that's different now is for elastic, kinetic energy is also conserved. The key thing with kinetic energy when we're doing the calculations is it doesn't matter if we have vectors. Because kinetic energy is a scalar, we don't have to worry about the angles and things like that we do with momentum. We just basically do the total kinetic energy of each object and compare them that way. So let's go through this example. This is one of the harder examples that you'd see. So it's a ballistic pendulum, which means you shoot a bullet into the wood, and the wood and the bullet would swing together, and by doing that we can then calculate how fast the bullet was going before it hit the wood. So part A is asking how would we calculate the velocity of the bullet. So the first thing you have to understand is let's calculate what the energy of the block is before and after. So once the bullet hits the block of wood and it's embedded into the block of the wood, so we have a mass of the bullet in the block at the bottom, so it's going to have some sort of amount of kinetic energy once the bullet gets it to move, and then it's going to swing upwards, so all of that kinetic gets converted to potential. So just like we did in physics 20, we can actually solve that. So we go 1/2 mv squared equals mgh. The masses don't matter, the bullet and the block of wood are the same for both sides, so we can actually just solve it for the velocity. So we plug in 2 times 9.81 times our height of 0.386, and we get a velocity of 2.75 meters per second. So that's the velocity of the block of wood when the bullet hits it. So just as it embeds into the wood, that's its speed when it hits. So now that we know sort of the final velocity, we can then figure out what the initial velocity of the bullet was. So we can use our conservation of momentum. So we have mass and velocity of the bullet plus mass and velocity of the block of wood will equal the combined mass and velocity after the collision. So our bullet, we know the mass was 0.202. Velocity is what we're looking for. The block of wood was 0 initially, and we'll have a total mass of 5.77 times that velocity that we just calculated, 2.75, and we can solve it then for the velocity of the bullet is 794 meters per second. So that's part A. So we've calculated the velocity of the bullet before it hits the block of wood just by using conservation momentum. So now part B, what we want to do is figure out what is, if the collision was inelastic or elastic or not. So let me just erase this part. We don't need this here anymore. So let's calculate our kinetic energy before and after. So our kinetic energy of the bullet before it hits the wood will be 1/2 mv squared. So we'd go 1/2 times the mass of the bullet was 0.02, and our velocity was 794. So we calculate the mass, the kinetic energy of the bullet, it's 6304 in energies in joules. Our energy of the block of wood is 0 because it wasn't moving, so we just have our 6304. And then our energy after will be the block of wood and the bullet together. So we'd have 1/2 times the total mass, 5.77, times our total speed, squared, and we get a total kinetic energy of 21.8. So you can see very inelastic, right? Our total energy before was 6304, our total energy after is 2108, so most of the energy gets lost in the collision. So the key thing to understand is when a bullet hits a block of wood and they stick together, or any other kind of objects that stick together in a collision, we always say that those are completely or totally inelastic. If they stick together, pretty much all of the energy gets lost, so it's totally inelastic. Otherwise, if they bounce off each other, it's going to be somewhere in between. It's still inelastic, but not a total loss. So question C now is asking how much is lost and what the percentage would be. So this one's pretty straightforward. Just do some simple math. So if we want to figure out how much it was, the 6304 minus 21.8, which would give us, so if we subtract the total energy, we'll get 6282 joules. So that would be how much is lost. So the questions could be worded differently. They could say how much in energy is lost, so in this case 6282. It could ask what percent is lost or how much percent is left. And in either case, just do your total. So in this case, if we go 6282 over 6304, that'll give you 99.7. So that means 99.7% of the energy was lost in the collision. Or if it was asking how much was left, just do the reverse. You would go 21.8 over the total, and that should give you 0.3%. Right? If you lose 99.7, 0.3 remains. So just depending on how it's worded, you can always answer those questions. And that's it.